So this is lesson 5. I ended up recording, but there was no sound, so I'm going to pick up my writing. Hopefully it doesn't go too fast. This lesson starts to remind me that I need to find my formula sheet for Math 30. So your formula sheet is photocopied on lime green. Maybe find that, and we'll slide down here. Gonna take a look at 3 statements that we already know how to solve. We've been solving these statements using base work. So by writing writing the number as a base of the stated power. So I replaced 81 with 3 to the 4. I actually know that the x value will come up as 4. I replaced the 7 with a power of 7, 7 to the 1, so x is equal to 1. D was kind of interesting in that I have to generate 12 to some unknown power exponent. 12 to some unknown exponent is equal to 1. Well, what is that exponent? We need to remember that 12 to the 0 is actually equivalent to 1. So that's my x value of 1. So the page looks a little different than it normally does. I started off with class example 2, trying to figure out some little tricks of the trade. The value of 1 as an argument is interesting. B to some power is equal to 1. Well, that's B to the 0. So that generates my answer by replacing 1 with B to the exponent 0. So x is 0 because my bases are the same. Again, please excuse my B's and 6's look very similar. What happens if I try to take the log of B with respect to base B? Well, that's kind of fun. I'm trying to look for an x value that will give me that answer. So b to the 1 is equal to b to the x, which means that x is equal to 1. I have some very similar work to do down below, and I actually did class example 3 twice. I first did it in the conventional format. I moved the 2 over to the right-hand side, divide by 2, and then I said 8 to the exponent of x over 2 is equal to 512. Had to do a little bit of work to figure out what 8 raised to the power would be, but that's 8 raised to the power of 3. I'm then allowed to, because my bases are the same, drop my bases and say that x over 2 is equal to 3, which made x equal to 6. Now in the red up on the left, I want you to think about a rule that's coming, but that's coming tomorrow. And that is, I could have replaced the 512 right away with 8 to the 3. I'm wondering if you can see the connection or what we did with the 2 and the 3 to get a 6. And then I'll just slide over to this last example. The last example ended up being a square root statement. Square root statements we're getting really comfortable with. Replace the square root with an exponent 1/2. I need to write it in terms of base 5. 5 to the exponent 3 was equal to 1/2. Bring the exponents together, multiply those, so I get 3 over 2. And then I get the very comfortable statement of saying, hey, my bases are the same, x must be equal to 3 over 2. Now we have logs in the exponent position, but we are already getting really comfortable with evaluating logs. So I took a look at the exponent position and replaced the 25 already with a power of 5. So 25 is 5 squared. So the answer to the exponent position actually generates a 2. Remember, logs generate exponents. You should have seen that a number of times today already. So then I get 5 to the exponent 2, which is 25. And I think I'm starting to see a little bit of a pattern or a trick. I did the same kind of writing for the next example, log base 3, so that's in my exponent position, but I replaced the 27 already with 3 cubed. So log base 3 of 3 cubed, I get the exponent spit out, that's a 3. My exponent position becomes 3, and 3 to the 3 is 27. So based on what I've already seen, I actually come to know that when I take a base raised to a log statement which involves its base, I get the value of n. And the value of log a to the n is actually n. Watch that these n's aren't actually the same. So be careful with that. Now, there is something new in this lesson, and that's when I'm trying to evaluate arguments, log arguments that aren't perfect multiples of 5 or 2 or 6. We're getting pretty used to those. I know that log base, that 5 squared is 25 and 5 cubed is 125. So somewhere near the lower end of between 2 and 2.5, I think I could find 50. So I could play around with my calculator, log 2, or 5 to the 2, 5 to the 2.2, see how close to 50 I can get. But we want to find another method. Before we get to that other method, there's another log function on your calculator. So we already played around with log base 10. We found that log button on your calculator. So you could actually just type log 89, log 2000. Those aren't large challenges for your calculator. What is challenging is recognizing another log button. There is another log function on your calculator. It's known as natural log. And when we have a little bit of time, I might share the story of where base E came from. But natural log is very common in calculus and science. And it's right adjacent to your log button. Try taking the ln of 5 or the log base E of 5. See if you can make your calculator do that. Otherwise, you have the ln button. They're equivalent. And then the ln of E is actually 1. Now, what are we going to do with that earlier problem? We want to learn a new rule, and that new rule involves changing the base of identity. I know and you know that 5 squared is equal to 25. So when I'm looking to evaluate the log of 25 base 5, I know that that's 2. But try this exercise out on your calculator. The reason why this works will come out in the lesson for tomorrow. But go log 25 over log 5, or ln 25 over ln 5. That's the log or the ln of the argument divide by the log or the ln of the base respectively. And you find out that you actually get the same answer, which is great. I can try that again with another example. I know that 3 to the 5 is 243, so the value of the log would be 5. But I can try out that trick. Log of 243 divided by log of 3, or ln of 243 divided by ln of 3 will also both give me 5. Here's the rule. The rule is very, very important, and we'll use it a lot. I can evaluate log 4 of 1024 by simply taking the log base 10 of the argument divide by log base 10 of the base. I don't have to worry about how 4 and 1024 are related, and I can do the same with log base 2 of 1024 divide by log base 2 of 4. The same answer will actually appear from there. And we're going to try that rule out just below. So I've applied the rule log of the argument, log 221 divided by log 5. Throw it into your calculator, 3.35. Log of 1 over 1,000 divided by log of 2, 9.97. Just going to two significant digits, or 2 to the nearest hundredth. Do some rounding. The last one, that 3 stands out in front. It's 3 times the log base 10 of 512 divided by log of 7. And my calculator simply gives me my answer, and that's great. And again, my apologies, the audio didn't work the first time, so just running audio on my writing right now. Convert log base 6 of 216 to base 3. I can simply write it log base 3 of 216 over log base 3 of 6. Did the same thing for log 300. That was a number I could evaluate, but I could write it as base 5. Log base 5 of 300 divided by log base 5 of 10. That's the unwritten base. Now the last 3 examples I did the first one with the rule. I took the log of the argument. There's a minus sign out in front, so that stayed out in front. Minus log of 1 divided by 343. Make sure you close your brackets. Divide by log of 7. It's actually 3. In B, I saw some familiarity in that I have log base 6 and base 6 that I think will cancel out, so to speak. They're inverses of each other. So the 6 or the 216 I can write as 3, 6 to the power of 3. Evaluate that log statement. So my exponent becomes 3, which generates my 216. And then the last one, 49 and 7, just spoke really loudly to me. Replace the 49 with 7 squared. Raise the exponent 2 to the negative 5. Multiply that, that's negative 10. And then I've got log base 7 of 7 to the minus 10. I can simply read the exponent off. That's it for today's exercise. Try out the homework. Remember, we've got a quiz tomorrow on lesson 4, which we said is fundamental to understanding log.